In May 2005, a European project called IP NANOKER started. This project was launched into the nanotechnology, materials and new processes area of the 6th Framework Programme of the European Commission. The objective of IP NANOKER was the development of new nanostructured materials for top-end functional applications. 25 partners from 11 European countries had an 18.4 million euros budget and 4 years to make what could come out of IP NANOKER. But let's start with the project coordinator and the cornerstone of this project, material science.
Material science deals with the study of the properties of solid materials and how those properties are determined by the material's composition and structure, both at macroscopic and microscopic level.
Material science is a very general discipline involving very different types of materials: metals, polymers, ceramics or composites. However, IP NANOKER focused its efforts on specific types of materials with high potential: ceramic nanocomposites.
IP NANOKER could be successful thanks to an excellent previous knowledge of the participants, the main infrastructure available of the participants, companies and institutions, a very strong industrial commitment both of partners and of potential users, and of course dedication of the participants towards the cost frontier goals of IP NANOKER.
Noble Biocare is a medical devices group and the world leader in innovative aesthetic dental solutions.
During this IP NANOKER project, evaluation of the mechanical properties has been very important. No matter how good and impressive from an aesthetical point of view, if the mechanical properties is not good enough, it's useless for us. So we started to look at mechanical properties, and when we have reached high quality and we think that mechanical properties is good enough, we have turned the focus into the aesthetical parts instead.
Thales Alenia Space is the European leader in satellite systems.
For Earth and space observation, we design and build space telescopes. These telescopes are equipped with mirrors that can be built into different materials. We classically use zero dur, which is a glass ceramic material with very low thermal expansion at room temperature. We have strong skills in lightweighting this material, but its low resistance is a limitation.
We also use CESIC, which is a composite material produced by liquid infiltration of silicone inside carbon. CESIC presents high mechanical properties and low cryogenic thermal expansion associated to a manufacturing process which allows the production of very complicated shapes. However, its coefficient of thermal expansion is not null at room temperature. This is why Thales Alenia Space is looking for a material that combines high mechanical properties and null thermal expansion.
Fundición Nodular is one of the world's leaders for production of mill rolls.
Fundición Nodular is specialized in mill roll production, and particularly those qualities with a highly alloyed steel outer layer for high hardness and wear resistance. After going through heat treatment, machining of such rolls implies outstanding cutting tools, which are usually very expensive and subject to hard working conditions. Results are really promising and trustworthy so far. The new materials provide astonishing test results, and we hope that they can be used soon in a more industrial way.
In order to be able to fulfill the product requirements imposed by the project industrial partners, it was necessary to keep in mind the technological solutions available.
Industrial applications of ceramic nanocomposites are limited by two main roadblocks. The first and crucial bottleneck is that traditional consolidation techniques, such as cold pressing and sintering at high temperatures, hot pressing and hot isostatic pressing, have strong application limitations of not being able to retain the nanoscale grain size due to excessive grain growth during processing. The second bottleneck for industrial application of nanocomposite is due to the structural instability of nanoparticles arising from their high surface area and the lack of available nanocomposite powders ready to be processed by different techniques.
Kollorobia Research Center was founded in 1999. The main role of Kollorobia Research Center in IP NANOKER is concerned with the development and production of innovative nanoparticles, particularly through sol gel techniques.
There are many advantages in the use of sol gel or polyol approach. In fact, we can produce small particles of about 10–50 nanometers in size, with different chemical composition and chemical physical behavior. Talking about nanomaterials, hydroxyapatites was prepared with polyol methods in liquid dispersion and nanopowders. The shape and dimension of nanocrystals obtained are similar to natural bone content, so we can use them in scaffold and prosthesis development.
Materials for knee and hip implants must satisfy multiple properties. Some of them are related with material nature, such as chemical stability or biocompatibility, but others, like hardness or fracture resistance, will be determined by its microstructure. So, it's very important to design the final microstructure nano-nano, micro-nano, or even macro-micro-nano, taking in mind the requirements for these materials. The colloidal processing route allows to prepare materials with a final microstructure that cannot be prepared by other processing methods.
Spark plasma sintering offers interesting sintering effects starting from nanopowders. FCT System has turned it into its main technology.
SPS is taking advantage of in-situ heating of the powder compact itself. This is achieved by a Joule effect of the electrical current flowing directly through the powder. By the use of fast SPS, nanostructured powders often retain nanostructure. Potential decomposition or reaction of the powder can be suppressed.
The University of Stockholm is one of the IP NANOKER partners involved in the consolidation of nano-sized powders by SPS.
The possibility is very large, I think. I can foresee that we can make 6 to 10 cups per hour in an SPS machine. And the cups are actually a niche product which has quite a high price. So I think that could be used for commercial purposes.
High-velocity suspension flame spraying has proved to be an effective technique for improving the tribology of final components by means of nanostructured coatings. The University of Stuttgart is the partner responsible.
High-velocity suspension flame spraying is a thermal supersonic process where nanopowders dispersed in a suspension are injected into a very hot flame, get molten, get accelerated to supersonic speed, and are projected to a surface of a workpiece where they form a dense micro or nanostructured coating. The method allows mixing of metal, oxide and non-oxide phases. And it has the potential for creating entirely new layer composite materials.
So what will come after IP NANOKER?
During and also after the project execution, new research projects on similar materials in new application fields are or will be on the run. Especially dental and aerospace applications are of special interest in the future.
The consortium wants to thank
I'm especially grateful for the efforts the partners addressed to the preparation of the deliverables, the financial and the legal documents. To all of them, many thanks.